In this video, we will discuss the derivatives of inverse trig functions. So I want to start by letting y be sine inverse of x, and we are going to find this derivative. So we want to find dy dx. Okay, so as we've seen with inverse trig functions before, when I have an equation like this, we are more comfortable transforming it so it's in terms of sine rather than sine inverse. So if I rewrite this in terms of sine, the roles of the input and the output will get switched. So right now x is being inputted into sine inverse. It will be the output of sine, and the y is going to be the input. Okay, so now I have sine of y equals x. My goal is to find dy dx, so right now this is defined implicitly. I don't have the y isolated. Okay, so my idea is, well, why don't we differentiate implicitly? Why don't we differentiate implicitly? So you might be wondering, wait, we had the y by itself at the start. Why do this? The reason for that is, even though I had y isolated at the start, I don't know the derivative of sine inverse. So I'm kind of stuck there. So I need some other way to obtain it. That's why we're rearranging it like this, because I do know the derivative of sine. All right, so I'm just giving myself some more room here. We had sine of y equal to x. We're going to differentiate implicitly, so let's take a d dx of both sides. So d dx of both sides. So on the right-hand side, this is just a normal derivative because I'm taking the derivative with respect to x. And the variable here, the x, they're the same. That means it's a normal derivative. That's going to be 1. On the other side, we're going to have to use some chain rule. The outside function is sine. Its derivative is cosine, so I'll get cosine, and I keep the same inside function plugged in. But then the chain rule says, okay, now multiply that by the derivative of the inside. And for the derivative of the inside, it's not just going to be 1, because these are different variables. I'm taking the derivative with respect to x, but that's the variable y. So that derivative is just dy dx. That's how I write the derivative of y. Okay, so let's isolate dy dx. Dy dx equals 1 over cosine of y. And I do have this formula now for dy dx. The only thing that I don't quite like about this is in terms of the variable y, but in the original function, the only variable was x. Or it was in terms of the variable x. It was y equals sine inverse of x. Okay, so our original function was in terms of x, so we want our derivative to also be in terms of x, All right, so here's how we're going to go about that. I'm going to use the equation. Let's put this in a different color. So let's use the equation sine of y equals x to be able to figure out what cosine of y is. So the way I'm going to do this is I am going to draw a triangle, a right triangle, so I can use some trig. And y is an angle. So I'm going to let one of these other two angles in this right triangle be y. It doesn't matter which one. I can make it work either way. Okay, so I'll just make this angle be y. And sine, if I use SOHCAHTOA in a right triangle, sine is the opposite side over the hypotenuse. And I'm going to write x as a fraction. As a fraction, I can think of this as x over 1. So I need the opposite of hypotenuse to be equal to x over 1. And the simplest way to make that happen is to let the hypotenuse be 1, and to let the opposite side from y be x. So let's let the hypotenuse be 1, and the opposite side from y is this. I'm going to let that be x. Okay, so we're in business. So I have this missing side. Let me call that a. And we can find this with the Pythagorean theorem. I'll just write find with Pythag. Okay, so if I use Pythagorean theorem, we will get a squared plus x squared equals 1 squared. And if I isolate a, we will get a equals, well, 1 squared is 1, 1 minus x squared. I would square root it to get rid of the squared on the a. And normally when I square root both sides of an equation, I gotta put a plus or minus. Over here, I don't need a plus or minus, since our a is a length. Okay, all right, so we know what a is. A is gonna be the square root of 1 minus x squared. But now in this picture, if I go back to where we were with the dy dx, remember, it was 1 over cosine of y. 1 over cosine of y. So dy dx equals 1 over, now I can write down cosine of y. It's going to be the adjacent side over the hypotenuse. So the adjacent side is root 1 minus x squared over the hypotenuse, which is 1. Okay, and I get 1 over, something over 1 is just the something. So this whole denominator is just root 1 minus x squared. And that, I now have my derivative completely in terms of the variable x. Okay, so therefore, so there's a math symbol for therefore. I just want to introduce some shorthand. So it's 3 dots like this. This means therefore. Therefore, the derivative of sine inverse of x is equal to 1 over the square root of 1 minus x squared. All right, we've just shown this formula to be true. Okay, we can do something really similar to get, the other inverse trig derivatives. I'm just going to say what they are because the process is very similar. The derivative of cosine inverse is negative 1 over the square root of 1 minus x squared. So almost identical to the derivative of sine inverse, just opposite sign. The derivative of tangent inverse is 1 over 1 plus x squared. These are the most commonly these are the inverse trig derivatives that show up most often, I would say. So I'm just going to state these. If there's ever a scenario where you need a different inverse trig functions derivative, like secant or cosecant or cotangent, we could look those up in a table of integrals, or we could just derive them in this sort of way, like we did here. Okay, so for both of these, there are similar proofs. Similar proofs. All right, so that said, let's do an example now. Let's do an example taking for granted that we know these formulas. So the example says, we'll find the derivative of tangent inverse of square root of 16 over ex to the 4. Okay, so I see an outside function here, tangent inverse, and I see something plugged into it, this square root of this whole thing. So this is looking like chain rule. Looking like chain rule here. So if we do chain rule, this derivative, the chain rule says take the derivative of the outside function first. And the derivative of tangent inverse, I see it up here. It's a 1 over 1 plus x squared, but the chain rule says, well, don't write x there. Keep plugging in the same stuff, the same inside function in for the x. So I'm going to keep plugging in square root of 16 over e to the x to the 4. Okay, so that's the first part of chain rule. And then the next part of chain rule is you multiply this by the derivative of that inside, derivative of this thing. So to take the derivative of that root, it'll be helpful to rewrite the root as a 1/2 power. And then inside I got 16 over e to the x to the 4. I can get rid of the fraction if I rewrite it as 16. And if I bring the e term to the numerator, I get e to the negative x to the 4. Okay, so from here, this is looking hopefully not too bad now. Okay, so we end up with 1 over 1 plus, and when I square this term, it'll get rid of that root and give me 16 over e to the x to the 4. And for this derivative, I need chain rule. Okay, and the outside function involves this power, this 1/2. Let's bring that down. 1/2, and then I subtract 1 from the power to get negative 1/2. And we keep plugging the same inside thing in. So the 16e to the negative x to the 4. And then the chain rule says, well, multiply this by the derivative of the inside. Okay, so the 16 is multiplying this e term, so that'll stay there. I'll still have 16. And then times the derivative of this e term, which itself requires chain rule again. Okay, so e to the stuff, the derivative of e to the stuff is e to the stuff, e to the negative x to the 4. But then I gotta multiply that by the derivative of the stuff, the derivative of this exponent, which is negative 4x cubed. And let's close that. And there we have it. That is our derivative. So this problem actually had about, I think, 3 sort of nested chain rules inside of one another. So in terms of our goals for this section, we finished our last goal, which was coming up with formulas for the derivatives of inverse trig functions.